This is a production of Cornell University.
So can everybody hear me? Okay, good. So one thing I learned about having goats, they give you plenty of opportunity to talk about things to talk about in a seminar that's entertaining. So, so I'm going to talk to you a little bit about the personal and the societal perspectives of agriculture. It's not just about growing food. Everybody here is familiar with growing food, so I want to talk to you about some of my personal experiences and our family's personal experiences on the farm. I'm going to talk a little about the historical parts, how other cultures treat agriculture, our natural resources, our family, a little bit on nutrition, and I'm going to close off with the effects that I felt from climate change on our farm and some of the spectroscopy areas that we need to consider for adaptation practices. Okay, now how do I start?
That's just a blank slide. You need to go one more.
No, I need just there's a video. Here it is.
Imagine the Earth as an apple. If it were sliced into 4 pieces, 3 pieces would represent the Earth's bodies of water. 1 piece would represent land. If the remaining piece were sliced in half again, 1 piece would represent the land on Earth that is unsuitable or inhospitable for farming. This leaves 1/8 of the apple representing land that is used to live on and grow food. 3/4 of the remaining apple slice would represent soils too poor to produce food, or land covered by cities, roads, and buildings. The remaining piece, 1/32 of the apple, represents the portion of the earth where food can grow. This is our farmland. The thin peel of this slice represents the farmland's layer of topsoil where our food is grown. Every minute of every day, the United States loses about an acre of farmland. Over 70% of America's fruit, vegetables, and dairy products are produced on farms near cities that lie directly in the path of sprawling development. Sustainable practices and careful planning, such as farmland conservation, are needed to protect this precious resource for today and for the future.
Okay, so these are my 2 children. They're much older than this now. Mikey is now 270 pounds. Elle is almost as tall as I am. She's the center of our basketball team. But when I was their age, maybe a little bit older, the one thing I always wanted was to have a farm. You know, it was just something. And 16 years ago, my wife and I, we got that opportunity, so we bought a 102-acre farm just south of Danby. And then the house wasn't habitable, so we had to rebuild the house. And when that finished, we started farming the property. And so we have chickens and eggs. We used to have goats, a lot of cats. But I learned a lot, you know, from agriculture and how it helps me at Cornell running the lab. When I first came to the farm, I talked to my neighbor who was farming it, and his comment to me was that Cornell wasn't useful to him much anymore. And so when I got the opportunity to come back to Crops and Soil Science, I was at the USDA at the time, to direct the lab, I decided I was going to change that. I wanted our lab to be useful to farmers again. And so my experiences on the farm helped me to develop new methods, because the methods that are in place, except for the soil testing, was we were able to tell them what went wrong after it happened. And as a farmer, you want to know, what do I need to do to prevent it from happening in the first place? So we started developing methods for that. This is, I guess, a slide, or what we have on our soil health program. And it's a quote from Thomas Jefferson. He writes, "While the farmer holds the title to the land, actually it belongs to all the people, because civilization itself rests upon the soil." And sometimes, you know, when you farm it, you begin to appreciate the importance of soil in agriculture and what happens if we lose it. Why is it important? I've come to believe agriculture is important to us not only as a food source, but as a familiar experience, accessible to everyone that it can help us understand many aspects of life, nature, and science. Agriculture is a practice so rooted in reality that it can guide our decisions. So in this growing up this millennial age, I guess, we sometimes think we're sort of the center of the universe. Everything is right there for us. Whatever we want, we just turn it on. We want this news cable, now where we just switch the channel and everything's there for us. You realize that when you're farming, your life is guided by nature and what's around you. And you have to make decisions based on that. And you quickly learn that you're not the center of the universe anymore. Preparing for this presentation, I realized our country was founded not by lawyers, but by a bunch of farmers. So if you want to go back to the history of our country, and that's why I say maybe that's the reason it succeeded. They understood the laws of nature that guided their decisions. So here's a section taken out of the Declaration of Independence. The wording is kind of hard from back then, but I'll read it. When in the course of human events it becomes necessary for one people to dissolve their political bands which have connected them with another, and to assume among the powers of the earth the separate and equal station to which the laws of nature and of nature's God entitle them. A decent respect to the opinions of mankind requires that they should declare the cause which impel them to separate. Essentially, what they, probably from agriculture and understanding the laws of nature, they knew that the laws of nature and nature's God gave them the right to become an independent nation. That contributed to our forming an independent country. So I'm going to talk a little bit about how they felt about agriculture. Andrew Wolf wrote that the founding fathers believed that the first president of the United States, George Washington, John Adams, Thomas Jefferson, and James Madison, were revolutionary farmers as much as they were revolutionary politicians. They loved farming and gardening so much that they gave it prominence even when engaged in war and politics. Gardening or farming was central to their lives, and they were truly the first environmentalists. They believed independent small-scale farms, whoops, I'm going to go back. I'm going to highlight that. They believed independent small-scale farms were the building blocks of the nation. And one thing I became concerned about when I had a farm is that we're losing all of our small farms to industrial farming. And we need to find ways to go back to having more small-scale farms. We got to put things in balance. Andrew writes that Jefferson believed that agriculture should be the foundation of the American Republic rather than industry, that he put more importance to agriculture than to industry. George Washington studied and implemented improved farming methods throughout his life. In fact, he thought of himself first as a farmer. Washington read the latest works on agriculture and implemented the new husbandry methods using a variety of fertilization methods and crop rotation plans on his 5 farms. In interviews with the National Republic Radio, Andrew Wolf described the founding fathers as obsessed with manure. So George Washington had this, whoops, keep hitting this instead of the, had this building built to, for the storing of compost from dung for his gardens. Okay. So agriculture places one in direct contact with nature. It teaches us the laws of nature. You're forced to experience it firsthand. You have to adapt your life to the way things are. There is a cycle to it that we need to learn. It's just the way it is. So some history. Agriculture is all in, it's totally involved in our culture. From the soil health book, I read that in ancient writings such as the Bible, the book of Genesis, the word Adam means red soil. And that's the reason is in this description, human beings came from the soil because soil brought forth life. Some Native American Indian cultures treat the soil as a living good neighbor. They respect and revere it. And they talk about you should walk on the soil like you're walking on somebody's back. You know, you need to be very gentle with it. In one culture, people take water from a well. They first pour a portion of the water onto the ground to give the soil a drink first. That's how much they respect and revere the soil. In many of today's developing countries, people view using too much fertilizer as we may view taking illegal drugs. They see it as making the soil addicted. So they like to keep things in a natural way. And that's why I think it's good to support organic farming. We are converting one of our fields to an organic farm. And I know personally how hard it is to pick up all those rocks. Okay, it is not easy. So things about agriculture. How many of us put off studying for an exam or crammed the night before? We all did it, right? So and that's something but this approach doesn't work in agriculture. You can't procrastinate. You know, how many of us know a farmer that can put off milking his cows until Friday or the night before a test, the night before he wants to do the milking? He can't do that. Can we cram in the fall for a crop harvest? No, we have to plant in the spring. In the spring and the summer, you begin harvesting wood for the winter. When the weather is right, or you have 5 consecutive days of sun, and the hay is tall enough to harvest, that's the time you harvest hay. So your life is basically controlled by your climate and by your weather. You can't have it always the way you want it. And you learn that very quickly. So, some goat stories. The only good thing about having these goats, it gave me lots of good material. Okay. We had a couple of goats. Well, first of all, my son had problems with milk, with tolerance to milk. So I told my neighbor about maybe we'll try looking at getting some goats because I hear that was better for milk intolerance. 2 weeks later, 2 goats showed up, and I've never touched a goat before. Okay, they were pregnant, and they needed to be milked. So I had to quickly learn within hours how to milk a goat. We had no place to store them. But anyway, so two experiences I had with them was the 2 of the babies were born, and they couldn't milk off to the mother, so I had to bottle feed them. So it was getting down to 10 degrees one night. So I took them off of our bedroom, went down to get the milk, and came up, and they got out of the bathroom, and they were standing next to the bed. As soon as they see me open the door and come in, they jumped on the bed and started peeing. So anyway, fortunately, the plastic shipping container was still on the mattress. All the bedding was up against the headboard, against the wall, and they only nailed the sheet. But the worst part was when they seen me rush over to get them, they squatted down. You could see them trying to squeeze it all out before I got there. Now, they're only 2 weeks old. I mean, that's how mischievous goats are. Then when I was building that hut there, that plywood, I had it laid down on the ground. I was cutting it to length. As soon as I went to pick it up, they all jumped on it. They have this immense sense of knowing what's the worst thing they could do at that moment, okay? So the question is, some of our experiences in the reality of goats, they look so cute and innocent, don't they, right? They start out so small like it, but so what I learned from them is, how do you name a goat? So I learned from personal experiences, the first 2 names of all goats is exactly the same. When you name a goat, you give it its 3rd name. So in this case, this is that damn brown ears, okay? So the first 2 names for goats is that damn, and then you put their name onto it. So one thing I learned also about farming is, just as our culture is, at church, now I understand in the Bible why Jesus put the sheep on his right and the goats on his left. Okay, so there's just a lot of things about agriculture that you really learn firsthand the experience, okay? So I'll tell you a couple stories about my daughter. She was adopted. She's 11 now. She's going into 5th grade. But this year, I think she was in kindergarten. And she was a little bit autistic, so she couldn't speak till she was about 2nd year through kindergarten. And so the therapist told us we had to keep the animals because I noticed when she was with them, she would speak more. And so we had to keep them for therapy for her. So we wanted to think of getting rid of them. We were wondering how much was it going to cost to keep them. We weighed that against what she was learning, and we decided to keep them. And so when she was 4, the first thing she did when she had the chickens, she decided that before they could all go out free ranging, they all had to pass their flying test. And she gave them all flying lessons. Threw them up in the air, let them come down. Anyway, so then she taught her friends how to give chickens flying lessons. That was hilarious. So we're wondering, what is she learning? And so she's watching the Little Bill show. And Little Bill's there's 8 bunny rabbits from school that he wants to adopt into his apartment in Philadelphia. And his father tells him no, and he lists all the reasons. Well, Little Bill had already thought that problem's out, and he's got a solution for every one of them. Now his father's got no recourse left but to consider letting him have these 8 rabbits. Ella sees that happen on the TV. She looks up at the television to give Mr. Bill some advice, and she says, "No, no, no. Those rabbits will poop a lot." So by the age of 5, she has waste management and scaled down, right? I told this to my neighbor. I said, "She's really learning a lot from being on the farm." He says, "Yes. She already knows." She has now already, by the age of 5, has more insight than half of the faculty in the College of Agriculture. Okay, so one last story. She's now in 1st grade at South Hill, and she's always gets books on nature because she wants to be a naturalist. And she loves the woods, and she loves the animals. And so this girl gets a baby goat for her birthday. And it turns out that every day it would go into its hut in the wintertime, it would snow. So after several times this happening, the goat goes in the hut, it snows. The girl thinks she's got a goat that can forecast the weather. So the next time it goes into its hut, she calls up all the radio stations and the news companies, and they come down, and it didn't snow. She's devastated. So she goes into the hut to see why the goat was in there, and it didn't snow. Well, it turned out the goat had given birth to 2 baby kids, and that's why it had to go into the hut without it snowing. Well, I didn't catch on quick enough. My daughter turns to that front page, sizes up the horns on that goat. That goat, there was no access to a billy goat on the farm. There's no way that goat could have gotten pregnant. That author then had no credibility, right? She turns over to one of the previous pages, looks at the picture of the farm animals in the corner, and says, "Dad, that mouse doesn't belong there either." So as part of our culture, kids learn a lot, okay? Agriculture is a source of food. Micronutrient malnutrition affect over 2 billion people, resulting in poor health, including coronary heart disease. And so these are all the important reasons for agriculture. Agriculture is just more than a source of food and human nutrition. We have to deal with soil management and research in agriculture. But I found out is greatly affected by climate change. So farming has taught me the importance of keeping a system in balance. Whenever I failed to comply with the laws of nature and the system went out of balance, it didn't end well for me. Agricultural policy needs a combination of both theory and practice. And I'm very appreciative for my education at Cornell and so forth. But I also learned that a good education helps prevent us from being deceived by ignorance, and some sense of spirituality and understanding of the laws of nature and complying with them can help us from being deceived by our intellect. And when we're always surrounded by education, I think there's a tendency for us in academic institutions to think that our intellect is infallible. And the first thing I learned on a farm, when I got the farm, was my neighbor who was a farmer knew a lot more than I did. So I had a lot of theoretical practices, but I needed some common sense to go with it. So agriculture and climate change. So I'm going to explore the connections. So my expertise in analytical chemistry, that perspective, and how I understand climate change based as a spectroscopist. This is, at least in this Ithaca, New York, your life expectancy is much longer claiming to be the Son of God than it is if you come up or even propose the possibility that climate change may be due to natural causes. Okay, so but I'm going to tell you why, as a spectroscopist, why I think that it may be the case. Here's science of the founding fathers. This belief and experience meant that nature was the highest authority, overruling and vetoing any human authority. This point of view was encapsulated in the motto from the Royal Society, the premier scientific society in the world, nullus in verbra. In other words, on the words of no one. So in other words, check it out for yourself. So I've seen some of the evidence of this, and I decided it was important to check out for myself. And I have a pretty good background in chemistry and some in physical chemistry, so I started looking into this more deeply. Because how we approach climate change tells us what adaptive methods we need to use. If we use the wrong ones, it could end bad. So here's the mechanism for climate change. Basically, you have energy coming into the Earth, some of it leaving up into the atmosphere, and then some of it coming back down. And this back radiation, they say, is about 340 watts per meter squared, and so what's going out is 239. And so there's basically, we're accumulating a little more energy than what's going out. But what's the mechanism for it? So global warming and climate change are both real and serious issues that we need to address. I experienced them firsthand. But we need to be careful that we don't get blindsided by causes other than CO2. We need to get the mechanism of greenhouse effect correct. So the current model confuses the word thermal equilibrium with steady state. That's their first mistake. The second mistake is it only recognizes Kirchhoff's law and ignores the effect of thermal collisions. I'll explain these independently later. And Kirchhoff's law has got some flaws in it to begin with. We need to recognize that spectral displays that you see come off an instrument are distorted and can lead to erroneous conclusions. So all these things need to be taken into effect. When these circumstances are taken into consideration, it's possible that the amount of atmosphere needed to create the greenhouse effect would be reduced from 12 to 16,000 feet down to about 350 feet, resulting in thousands of feet of extra atmosphere not used to warm the atmosphere. So some of the limiting factor controlling global warming may not be CO2, but sunlight. So what the spectroscopy evidence suggests is that if this is 16,000 feet, and that is required, and there's still radiation getting up to that height, then adding more CO2 to the atmosphere would increase global warming. So human inactivity would have an effect. However, if the amount of CO2 if there's enough CO2 in the atmosphere at 350 feet to absorb all the radiation that's coming off the surface of the Earth, that's that infrared radiation, then all of this from here up to outer space is now extra. And so adding more to the natural extra that's already there is not going to change the outcome, or very little change to the outcome. So to begin with, some basic physical chemistry. There are 4 types of kinetic energy. Translational energy, which is thermal heat. Rotational energy, which we know as microwave energy. Vibrational energy, which is infrared. Electromagnetic radiation, which is the lights that you see. That's when electrons from an excited state go back to a ground state. So the Maxwell-Boltzmann equation for thermal equilibrium predicts the ratio of excited state of the electrons, both vibrational or rotational, to the ground state as a function of temperature. So right here, that's in degrees Kelvin. So this is your ground state. This is your excited state. So it says that when when there's excitation of CO2, this is going to get excited more as you get increased temperature. And this predicts how much it will be excited. So it's all based on excitation of your element, of your compound of interest by temperature. And so when you have radiation coming from the surface of the Earth plus temperature imposing on CO2, then the NB over NA becomes overpopulated. The amount of excited CO2 is now greater than what is predicted by this equation. That's why they should use the term steady state and not thermal equilibrium. I think this is if I mentioned, it's probably the most abused equation in science because nobody really understands. They use it without totally understanding what it means. So the global modeling is based on the assumption that the Earth's surface and the atmosphere being in thermal equilibrium. This is not the case because the equation holds true if the source of energy is thermal. In the case of global warming, we are dealing with both radiational energy and thermal energy. Also, these energies are in constant state of flux, so the system is at steady state, not thermal equilibrium. So for the excited state of CO2 at the 4 micron peak, it's about 0.03%. At the 15 micron peak, it's about 2%. If you plug about 300 degrees Kelvin or 270 degrees Kelvin in that is for temperature. So when CO2 absorbs infrared radiation from the surface of the Earth, the excited state becomes overpopulated, keeping it from being in thermal equilibrium. The mechanism for global warming is based on Kirchhoff's law. And that is a good absorber of radiation is also a good emitter of radiation. And for the most part, that's generally true. But infrared radiation, IR radiation radiating from the surface of the Earth is absorbed by CO2. The CO2 then becomes excited. And then it releases the infrared radiation in all directions. The Earth absorbs some of the radiation, converting it back to blackbody radiation. Then warming of the air happens through convection. So essentially, the radiation is coming up from the Earth. It hits the CO2. The CO2 absorbs that radiation from one direction, but it releases it in all directions. Because the ground absorbs that radiation, there's a net direction down towards the Earth. So there's less of it going up the atmosphere, more of it's coming down to the Earth. And that's where they get that forcing mechanism and what they call the greenhouse effect. But there's some problems with that. What they didn't take into account is the fact that nitrogen and oxygen are colliding with that excited CO2 at a rate of about 3 billion times a second. So at that point, instead of just the radiation warming the ground, it directly warms the air around it. So under those conditions, instead of needing a lot of atmosphere to direct the light back down to the Earth, you only need a much smaller volume of atmosphere, making more accessible in excess. So what they say is that when you look at this spectrum here, there's a serious problem here. Does anybody know what it is? The tops of these things are all flat. Does anybody know why that is? It's basically because the radiation from the ground isn't getting to outer space. It's all absorbed. The other thing you notice is that water makes up about 98% of the greenhouse gases. So all the shaded areas here is energy that's being absorbed and warming the Earth. All the white areas here is the emission going back to outer space, cooling the Earth. And what makes it whether go warm or cold is how these things are kept in balance. So if this is already saturated, adding more, how much is that going to affect global warming? Is that going to increase global warming by adding more CO2 when it's already saturated? And that depends on the altitude that all this takes place at. And that's the one thing that we don't have a direct measure of. Okay? So this is a paper by Hung and Barrett versus the IPCC. And here's what it shows. Some very interesting results. So you see this first curve here. This is CO2 alone in an ampule, in a vial, or a cuvette. And it absorbs this much radiation. When you add helium to it, it absorbs more radiation. When you add nitrogen to it, the radiation that it absorbs is 3 times more. So that means that when CO2 is colliding with nitrogen and oxygen, it's making more CO2 atoms or molecules available for absorption, increasing its efficiency as a greenhouse gas. Meaning, again, you need less atmosphere than what's predicted if you only look at the Kirchhoff mechanism. So the IPCC claims that the doubling of CO2 concentration would widen the absorption spectrum for CO2. And that's this area between the pink and the black line that I put in. Okay, so this spectrum comes down and it widens out at the bottom. And what they're saying is that, well, if you double the CO2, then this white area where the light or the radiation escaped outer space would get smaller because this would start to fill in with the CO2 absorption. And I don't think that's going to happen. And from a spectroscopist's point of view, we know that these images have distortions in them. And so you can't directly, you have to realize that this absorption peak is actually wider than what's displayed. So there's a lot of distortions in these spectrometers, and you need to be aware of that when you do your calculations. So what they're saying is that the IPCC is saying that this would account for an additional 4.3 watts per meter square of energy coming back to the Earth. And I'm saying that's probably not going to happen, and I'll explain why. So here's, I'm sorry about this slide, I'm not very good at PowerPoint. But if you were to have a perfect spectrometer that was going to image exactly the radiation pattern that is entering it, what you would have would be these straight blue, green, and red lines with nothing in the middle. Okay, but when the light enters into a spectrometer, it gets distorted because of the grading, the width of the entrance slit, the width of the exit slit, the lenses, whatever is used to image the light or the energy coming in, it ends up being distorted. So it shifts it to the left and to the right. So you see this line here, this is it. Let's say this green light is 500 nanometers. So the emission coming at 495 is not a wavelength of 495. It's a wavelength of 500 that has been displayed at 495. So that means when you look at these spectra, the only part that's accurate part of the spectrum is what's exactly in the center. And what's on the edges is distortions, and you need to keep that in mind when you're making your interpretation. So here's what happens. It's sort of like this. Here's me throwing a basketball. And you notice that when you take a picture of it, because you can't have an instant image, it gets distorted. Okay? Here's a close-up of it. Okay? This same effect is the same thing that happens inside a spectrometer. So you've got to understand this when you do when you run calculations. So the IPCC claims that this doubling would be 4.3, and I'm saying the reason this peak is narrow and is not matching the black line is because the radiation in the white areas is spilling over into it, preventing it from being as wide as it really would be displayed if we had a perfect spectrometer. And so, so that Dr. Heinz Hung did an experiment. He used a high-res instrument. And his conclusions was that the amount of additional radiation coming back to the Earth if you doubled CO2 would be this small edges here and here. And that the forcing would be only 0.054 watts per meter squared, rather than the 4.3 that's predicted by the IPCC. Okay? So the global warming is going to be a lot less if you increase CO2 in the atmosphere. I had trouble finding any place that explained exactly how they do the calculations. So I found this paper by the American Chemical Society that gave it an attempt at explaining it. And what bothered me was the fact that it says this figure simulates what would happen if you had an imaginary atmosphere. So I'm not sure, how did they do their measurements? Did they just take direct measurements? Or did they just do a simulation to come up with these numbers that they're using for what's going to happen if we increase CO2 in our atmosphere? How much is the temperature going to change? I'm not comfortable if people are just doing simulations rather than direct measurements. They're saying that the red line is wider than the blue line based on a simulation. I don't know. So I don't think there is enough evidence to come to a definitive conclusion. The material presented here needs to be given serious consideration, and not we just accept the dogma that's out there. To resolve this issue, we need a direct measure and not a model for the amount of atmosphere needed to create the greenhouse effect, and know how much of the atmosphere is extra. This is important because we need to know which adaptive strategies and policies we need to implement. That's really critical for agriculture. The experiment we need to perform. We need to know the concentration of CO2 at different locations around the Earth. But is the amount of CO2 in the atmosphere the limiting factor, or is radiation from the sun limiting? If we add more CO2 to the atmosphere, will it add to the greenhouse effect? Depends on the altitude you have to go before all the radiation from the Earth is absorbed. We need an experiment that measures the radiation from the Earth that is absorbed by CO2 at different elevations in the Earth's atmosphere. One of the technical problems with infrared radiation and measuring it is that the infrared radiation also comes from the instrument itself and from the detector. So the detector is measuring its own radiation. So technically, you need to get the instrument chilled to like a minus 40 degrees, so that when you're doing your experiment, the filament is about the same temperature as the surface of the Earth at 15 degrees. If you don't chill the instrument, then you can't see a difference. Okay, so this is Beer's law, and it talks about how anything is absorbed, how it goes straight, and then it begins to tail off. So if CO2 absorbs goes about to 95%, exceeds at 12,000 feet, adding more anthropologic CO2 would cause global warming, because this will continue up very slowly, okay? And so if it takes all 12,000 to 16,000 feet, adding more CO2 by us would make an effect. If CO2 absorption falls off at about 350 feet, more CO2 won't really matter. It would all be extra. And it would be like having a sponge pick up 1 teaspoon water. Adding 10 sponges isn't going to pick up any more water, because you already absorbed all of it, or almost all of it. So here's my experiment. Now let's see if this works. Okay, you block out so it starts off with a laser, which is the source of radiation. So you replace that with a light tube, turn it upside down, face it towards the Earth. You put it into a minus 40 degree box. For some reason that didn't turn around, but anyways. So you'll have to turn the helicopter around, I guess. So anyway, so now aim it down. Then you come in with a, where's the crane? Okay, wait a minute, where's the helicopter? Okay, there it is. Okay, so helicopter comes in. And now it's supposed to fly off. There it goes. Okay, so I think this is an experiment we need to do. So we know exactly where that absorption takes place at. This was in case the previous slide didn't work. Okay, so let's say we need to know here, and at what point does the absorption go to nearly to zero? That's a really critical measurement that we don't have. as that goes up. Okay, so I just want to give you some perspective of the historical record that we have. So here we have high levels of CO2 gradually coming down. And then we have the temperature of the Earth. So here the oceans froze over, it warmed up. And right now we're over here. Okay, so we are still in the Ice Age. Now this is the same thing, but it's on a log scale. So it amplifies the recent history. So you can see recently we've had climate change going on for a long time. Now it's trending up. But look what the trends have been before. I mean, climate change is something that's been going on for millions of years. And I don't think there's any reason to expect that this is always going to be the new norm or what we're experiencing today. So climate change gives us a real challenge for growing more food because it makes it harder. It does make it harder to grow food. So this is why I think adaptation becomes so important. That's why I'm so enthusiastic about the soil health program. Because if you don't take good care of the soil, you lose it. You're not going to be able to grow crops when you have issues with climate change. You have too much water or too little, it's going to be hard to grow food. So here's a no-till farm. It's much better practice. It absorbs water through the soil. It stores water in the groundwater. The soil doesn't run off, and you can grow more food. We need to use molecular biology to grow aluminum-tolerant plants that can withstand weathering in various conditions, so we can grow food in more arid lands. We need to use greenhouse operations. The tomatoes from back there came from our greenhouse operation. What I learned in using controlled environmental agriculture, you can actually grow very good tasting tomatoes because I can isolate it from the environment. I can control disease without using pesticides or fungicides or herbicides or any chemicals. You start them in January and they outgrow the disease, and so I don't need to grow the genetically modified tasteless tomatoes. Right? I can actually grow good tasting ones and sell them locally. So I think this needs to be more advanced. So here's my daughter and her friend. They're planting seeds in pots in the greenhouse. I want to see if this will play. Let's see, I'm not sure how to, let me go back. This is kind of nice on what a farmer is. I don't know how to do it. Okay. So this is the end of the slide, and I hope this is the future generation of agriculture. So take any questions anybody has. Any questions? Yeah, Randy.
I think you should suggest to Manaloa to do your experiment.
To what?
To the people in Manaloa.
Yeah.
That because they have the temperature and the CO2 concentration at the exact same time. So they know where the window is.
Yeah.
And they know how the CO2 concentration is changing at any given time. And they can.
Yeah, we also need to know what it is over the oceans. We need to know what it's over land. Right? At what altitude does our atmosphere absorb all that infrared radiation? I mean, that's the crux of the whole problem. And I think, was it, not Hemingway, from where it said there's lies, damnable lies, and then there's statistics. And maybe we should then extend that to computer modeling. You know, if you don't have the numbers right, you don't understand your system, then it becomes hard to give an accurate prediction. Any other questions? Yeah.
Yeah, I think we have to revise a little bit your story of the American Declaration of Independence. I mean, George Washington may have been a farmer, but how many slaves did he have actually tilling? And how much was he himself tilling? We all know about Jefferson. He did have this idealism, and John Adams was sitting up there in Boston. He was a lawyer. So I don't quite get that. And then the Declaration of Independence was primarily, as we now know, about because Britain was about to abolish slavery, because the king was dealing with the Indians fairly, Native Americans fairly, and because he let the Quebecers keep their Catholic religion. If you read in the Declaration of Independence the list of grievances against the king, you're going to see this part you put was just window dressing. So I think we can't just let that go by.
Okay, thanks for bringing that up. Other questions?
Would you go back to the slide that has the window where the Earth is radiating?
That's going back the wrong way, I'm sorry.
Radiation.
Oops.
That one, but the one before it, the one before we had the window.
That one?
The one like that, but it had a window of radiation. Maybe back 5 slides. Oh, you just, okay, keep it the other way.
This one?
Next one. Next one.
What?
One more. I'll keep going. Oh, no, the other way. I that one.
Okay.
Where's the window where the Earth is radiating, at the temperature of the Earth?
So the Earth is radiating in all of the areas that are in white. What? That's the blackbody radiation.
It's a tiny fraction. Where's it peaking?
Yeah.
Okay, so
Like if you put the Planck function up there, where would it peak?
what?
If you put the Planck function up there, where would it peak?
So this is inverted because this is looking at,
But I'm asking if you actually look at the emissions from the surface of the Earth,
yes,
using a blackbody curve,
right.
where would it peak on that x-axis?
You can't do that here because
Why not?
the absorption,
Function gives you irradiance as a function of wavelength.
right.
There's some very standard, entry-level textbooks that have those two diagrams juxtaposed. You can see
I don't
where
have,
the blackbody emissions peak from a
right,
sort of terrestrial temperature.
yes.
So where would that be on that diagram? Because that's important, because it tells you where the peak radiation from the Earth would be.
Yeah, it's not on this diagram because this is an absorption spectrum.
No, but it'd be about 10 microns.
It's like 15.
15 microns.
So it's right where the CO2 sits.
Right, and this is where also where the water sits. And you also have another far,
And what pressure level is this?
I believe this is at atmospheric pressure or throughout the atmosphere. So it's going to be low pressure to high pressure.
This is the surface pressure.
Well, some of it's going to be surface, some of it's also going to be a result up in the upper atmosphere.
So you're saying it's vertically integrated.
Yeah, it's vertically integrated from the surface of the Earth to outer
It's very
space.
different if you go up to the, say, 11 kilometer height.
Yes.
That's a big jump. And the absorption of CO2 is hot, still up there.
Well, the question becomes, does the CO2 radiation, does the radiation from the Earth that CO2 can capture, does it get that high to begin with? That's the important question.
Peak is right at the same center point almost as the CO2.
Right?
Water vapor window that you alluded to is slightly to the left, which is not where Earth is emitting most of its radiation. The other one that you alluded to, widening, is actually not a major emission temperature or a radius band of the Earth's surface. So I think glossing over those details is a little misleading.
Yeah, well, I don't have the slide that I put in here. It's too many, so I didn't have the slide.
It's not so misleading in terms of what your story is, because the peak around 4 microns is really irrelevant. It doesn't matter if it.
There's not much incoming, there's not much outgoing
That's
at
right.
that frequency.
That's right.
Yeah. That's like where the solar radiation and the Earth radiation cross. Both close to zero.
So the only peak that's really important is the one near 15 nanometers, which is about right in the center of the CO2.
Yeah, exactly.
So where it's saturating.
Yeah.
But still
And
saturated.
actually methane, which is over there by 4, the kind of dark,
Someplace over.
is irrelevant too in this story.
CO2. But one thing to keep in mind is the energy at this end of the spectrum is much greater than the energy at this end of the spectrum.
Yeah, but the Earth is emitting almost nothing.
No.
It's the solar mostly, and the absorption by the water vapor in the atmosphere. So I totally agree, and that's why we get solar radiation absorbed in the atmosphere. But the peak of the Earth radiation being centered on CO2 is really an important part of the story. And if you go forward to your paleoclimate slides, that's a very outdated curve that you showed. There's been a lot of work since then.
Yeah, this
Trying to, the paleoclimate, so you went through glacial, interglacial times.
yeah, I'm basically limited to what I can
So you
do.
went back to the Cambrian.
Yeah,
And it's true that there were cold climates in the past, and that major dip that occurs right at the end of the Ordovician is well known, and also the Permian extinction. These are well known events to have correlated, especially that second one. To go back to the end of the, basically the Permian, the end of the Carboniferous.
so
300 million years. Carboniferous. And the Carboniferous is named because of the drawdown of CO2 by terrestrial plants, which is linked to widespread glaciation, which actually supports the hypothesis of a strong correlation between CO2 and climate through time. I totally agree. In the last 500,000 years, we've been in an ice-like climate on average. But the numbers in terms of actual temperature increase that we're talking about during the period of the dinosaurs is, I mean, it's very dramatic.
right.
It correlates with CO2, and it would have huge consequences for agriculture.
Yes, it would. I don't doubt it, but
And it matters that it's CO2 because there's something we can do about it.
yeah, there's something that we can do about, but then it all comes down to this one basic answer which we don't have. How much of it in the atmosphere do we need that's causing the climate change? Is it this much or is it this much? That's the critical spectroscopic answer that we have to have made.
It's not make it sound like a difference between 4 watts per disparity and 0.05 watts per disparity. That's a huge difference in terms of the amount.
That's right.
That's not the uncertainty, though. That's not even accurate in paleoclimate context in the last few millions of years. And it's not supported by the preponderance of evidence that comes from different types of modeling observational systems. That's not the real uncertainty. The real uncertainty is probably in, on the order of 2 to 4 degrees per delta.
But how did they arrive at those watts per meter squared? Did they use the wrong assumptions from the spectroscopy curves? That's the question that I'm bringing up.
That's just one method. You can get a similar estimate if you look at, you cited Euler, who was a climate change skeptic for a while until he developed his own reconstruction of global temperatures going back to the 1700s. You showed the curve from Euler 2012. If you use that time series of global average temperatures and the volcanic eruptions, you get a sensitivity of the radiative term of about saying 3.5, 3.7 watts per square. Now that's volcanoes, but it's still radiative forcing. Now the radiative forcing from CO2 you can get either from the models like you cited, or it could be from paleoclimate evidence, which puts you about the same ballpark. You can do it from a simple energy balance model. So there's multiple avenues that give us this 2 to 4 degree estimate, and those are well known. And to gloss over that, I think is not an accurate portrayal of the science, the state of the science.
Would you like to use the board and give us the derivation of the forcing constant?
Which one?
For CO2.
I don't know it off the top of my head.
I don't think anyone does.
I don't know it off the top of my head.
Okay, I'm gonna call time here. We are over time.
But there's articles here that people are welcome to read. I have copies of them if they want to go through some of the, look at it from both sides.
Okay, please thank Mike and the roll.
This has been a production of Cornell University, on the web at cornell.edu.